Welcome to part 2 of Bayes' rule. Over the next few minutes we will derive the equation that embodies Bayes' rule and see how it can be used to decide whether a patient has smallpox or chickenpox. But first we need to define a crucial bit of mathematical notation. As a reminder, in part 1 we used Bayes' rule to decide whether having spots means you have smallpox or chickenpox. From part 1 we already know that the probability that you have spots given that you have smallpox is 90% or 0.9. Because the value of this probability depends on the fact that you have smallpox, it is called a conditional probability, and it is written using a succinct notation as shown here. This equation is to be read as the probability that you have spots given that you have smallpox. So the vertical bar is just a shorthand for given that. We can derive Bayes' rule by representing probability as area. In this example, we assume there are only two possible categories of diseases, smallpox and chickenpox, represented along the vertical axis. We also assume there are only two possible categories for symptoms, spots and no spots, represented along the horizontal axis. If we assume you're just a person chosen at random from the general population, then the area of box A represents the probability that you have smallpox and that you also have spots. Box B represents the probability that you have smallpox and no spots. Box C represents the probability that you have chickenpox and spots. Finally, box D represents the probability that you have chickenpox and no spots. Now we can combine these probabilities to obtain the conditional probability that you have spots given that you have smallpox. The general strategy we will use to derive Bayes' rule involves two stages. First, we derive two different expressions for the area labelled as A, which is the probability of having smallpox and spots. Second, we combine these two expressions to obtain an expression for Bayes' rule. As we have just seen, the probability that you have smallpox and that you also have spots is given by the area of box A, as shown in equation 1. The overall probability that you have smallpox is given by the area of this orange region, which is A plus B, as shown in equation 2. Now, the conditional probability that you have spots given that you have smallpox is the area A expressed as a proportion of area A plus B, as shown in equation 3. You might want to pause at this point to convince yourself of the truth of equation 3. If we multiply equation 3 by equation 2, then we obtain equation 4. And if we cancel the term A plus B on the right hand side, then that leaves A. For convenience, we rewrite equation 4 like this. We now have our first expression for the area A. We find the second expression for the area A as follows. As before, the probability that you have smallpox and spots is represented by the area A. The overall probability that you have spots is given by the orange region, which is A plus C, as shown in equation 6. The conditional probability that you have smallpox given that you have spots is the area A expressed as a proportion of A plus C, as shown in equation 7. If we multiply equation 6 by equation 7, then we obtain equation 8. And if we cancel the term A plus C on the right hand side, then that leaves A. For convenience, we rewrite equation 8 like this. We now have our second expression for the area A. We now have two expressions for the area A. From equation 8 we have this, and from equation 5 we have this. Therefore, equations 5 and 8 are the same. But the quantity we are really interested in is the probability that you have smallpox given that you have spots. This can be obtained if we divide both sides by the probability that you have spots, where this cancels on the left-hand side, which yields Bayes' rule applied to smallpox. This says that the probability that you have smallpox, given that you have spots, is the conditional probability that you have spots, given that you have smallpox, multiplied by the probability that you have smallpox, all divided by the probability that you have spots. We have just derived Bayes' rule applied to smallpox, but the same logic applies to chickenpox. This says that the probability that you have chickenpox, given that you have spots, is the conditional probability that you have spots, given that you have chickenpox, multiplied by the probability that you have chickenpox, all divided by the probability that you have spots. Now that we have derived Bayes' rule, we can plug in some numbers to see Bayes' rule in action as follows. First, let's use Bayes' rule to find the probability that you have smallpox. We know the probability of spots given smallpox is 0.9, and that the probability of smallpox in the population is 0.001 or 0.1%. We also need to know the prevalence of spots in the population, which is 0.081 or about 8%. Putting all these together, Bayes' rule provides the probability of smallpox given spots as 0.01 or 1%. Next, let's use Bayes' rule to find the probability that you have chickenpox. We know the probability of spots given chickenpox is 0.8, and that the prevalence of chickenpox in the population is 0.1. As before, the prevalence of spots in the population is 0.081. Putting all these together, Bayes' rule provides the probability of chickenpox given spots as 0.99 or 99%. To summarize the last few slides, we now have Bayes' rule applied to smallpox and chickenpox. Of course, this applies to any disease and any symptoms. Finally, if we represent disease as D and symptoms as S, then we obtain Bayes' rule in its most general form. Each term in Bayes' rule has its own name. The probability of having each disease given certain symptoms is called its posterior probability. The probability of certain symptoms given a particular disease is called the likelihood. The probability of each disease is called its prior probability, and the probability of having certain symptoms is called the marginal likelihood. Using these labels, Bayes' rule is sometimes written like this. This says the posterior is equal to the likelihood multiplied by the prior, all divided by the marginal likelihood. The reason this matters is because we usually know the likelihood, for example the probability of spots given that you have smallpox, which is not what we're interested in. But we rarely know the posterior, the probability of smallpox given that you have spots, which is what we are interested in. In essence, Bayes' rule matters because it provides a method for transforming the uninteresting likelihoods that we know but do not much care about into the interesting posteriors that we do not know but care a great deal about. This is just one of the examples from my book called Bayes' Rule, A Tutorial Introduction to Bayesian Analysis. Chapter 1 and computer code which implements the various examples in the book can be downloaded from the book website. 4 versions of the book are available, which contain code in Python, MatLab and R. These books are available on Amazon in hardback, paperback and as an e-book. Thank you.